Okay, the second part of the second postulate of special theory of relativity is that the speed of light is always the speed of light in a vacuum, and nothing can go faster than that. And so this means, not just what we see as visible light, but this is true for gamma rays, radio waves. You can sing the song if you want. They all travel at the speed of light. But we know that light is a wave for sure, but also light is particles, and we don't study that very detailed in this course, but trust me when I say that's true. And light, visible light, and including the rest of the electromagnetic spectrum, is carried by the photon. So the photon is the particle for electromagnetic waves. And so photons travel at the speed of light. Photons have zero mass. So when we talk about the speed of light, well, it's not just light. Any particle that has no mass, and there are other particles that have no mass. Don't ask me to name one right now, but there are. They all travel at the speed of light. And in fact, that is a property of particles with no mass, that they travel at the speed of light. The speed of light that we know of, which is 300,000 kilometers per second, or 3 times 10 to the 8 meters per second, that's true in a vacuum, which is like outer space, no air, nothing. In air, like near the atmosphere, like in our atmosphere, Earth's atmosphere, it's still pretty close to that. It's not changed much. But if light travels through another medium, it might be slowed down a little bit more. Light never goes faster than 300,000 kilometers per second, but it can go slower if it's in a different medium, like water, for example, would travel slower. Part of that idea, and this is to do with relative velocity, and this is all stuff Einstein came up with, and it's crazy stuff, and it doesn't make any sense, but it's all true and been shown by experiment, not just because Einstein said so, but people have since experimented with these things to show that it's true. If you had a car driving down the highway at 100 kilometers per hour, and that car has its headlights on, you might normally think, to use a different frame of reference, if you're in that car and you throw something forward out the window at, say, you can throw something at 5 kilometers per hour, so you're driving at 100, you throw something away from you with another 5 kilometers per hour, that thing is moving at 105. You might say that's true for the light then. Light, if you're in your car driving 100 kilometers per hour and you're shining your headlights, then that light must be traveling 100 kilometers per hour plus the speed of light. But in fact, that's not true. All studies show it's just the speed of light. There's no relativity doesn't work for the speed of light. It's just 300,000 kilometers per second. It just is. And then, like, even weirder than that, I think, and I got two examples. The first one's just the obvious. Say you're walking towards that car. So you're walking in the opposite direction of the car at 100,000 kilometers per hour, or 100 kilometers per hour. You're going 5 kilometers per hour. Then you might say that the relative velocity, the gap between you and that car, is closing at 105, right? The car's 100 and you're 5, and so you're moving towards each other at 105. So then you might say then that the light moving relative to you as you walk towards it must be, because the car's going 105 kilometers per hour, you might say to yourself, well, the light must be traveling at speed of light plus 5, right? And it's not. And it's not. It's just incredible. The speed of light is traveling. The light is traveling towards you at the speed of light, even though you're closing the gap. And to give even a better example, which is just mind-blowing, when you're driving down the highway towards, and then you're kind of, hopefully not had a head-on collision, but coming towards another car, and that car is shining its lights towards your car at the speed of light, and your car is shining lights at, in the other direction at the speed of light, you would think the gap between the light of those two cars should be closing at 2 times the speed of light. And it's not. Again, experiment has shown it's only closing at a rate of the speed of light. Even though the gap between you and the other car, maybe 200 kilometers per hour, it's doubled, but the light gap is still only closing at the speed of light. And if you think about that for a little while, it's mind-boggling, completely mind-boggling. Counterintuitive, modern physics. Oh, I forgot I had this question. So there's the answer. Huh? This is proton A. Okay, this is the two cars, right? It closes with the gap. That's what I was talking about. Okay, now you have two protons. So this is what they've done lots of times in what are they called? Particle accelerators. So you have one proton traveling in a particle accelerator at 0.9 c, 90% the speed of light west. Proton B is 0.9 c in the east. And it says, what is the proton's velocity, B's velocity with respect to A? So how does A see B? A is moving west. Theoretically, B should be moving at 1.8 c towards it. The gap should be closing at 1.8 c, but it doesn't. It's closing at the speed of light because nothing can be greater than the speed of light. And again, they've shown this time and again in experiment. It's unbelievable. And the inexplicable, like the undoubtable conclusion, which we'll talk about later, is that, okay, speed of light's constant. Either time's changing or space is changing. One of them is changing because of the three things of distance, space, and time, distance, time, and speed of light, and speed, there's a constant relationship there. And if it's not the speed changing, then distance and time must be. And time and space warp to manage the speed of light. And that's what Einstein's special theory of relativity says. And we'll get into that lesson coming up. Okay, one more little. This is that same tabletop guy. I just gotta fast forward.
Something can't tell you.
I've seen that. Let's get to here.
Okay then. Let's go to a parade. You're throwing candy to onlookers, and normally you throw candy at 5 miles an hour relative to yourself. The truck is trotting along at 2 miles an hour. So when you throw candy to people behind the truck, you are throwing opposite the truck's motion, and the candy reaches them traveling slower than it would if you were standing still relative to them. How much slower? Well, you subtract the truck's speed from that of your throw and find 3 miles an hour. When you throw the candy forward, it's moving with the truck, and so hits the spectators going 7 miles an hour, your pitching speed plus that of the truck. Got it? Good, because now things get weird. Light, it turns out, is special. It doesn't behave like candy, trucks, baseballs, or any material object for that matter. See what I mean? Let's wait for nightfall. Now imagine you're standing still next to a stationary truck. We can think of the light coming from the headlights as little particles or waves. Take your pick. What's important is that we measure how fast they're leaving the truck. This is like your pitching speed at the parade. When we do this, we find the light is leaving at 670 million miles an hour. Now, let's have the truck zoom towards us at 10 miles an hour and measure the speed of the light leaving the headlights. How fast do you think it's going? 670 million miles an hour plus 10? Well, that would be wrong. No matter what, we measure the speed of light to be 670 million miles an hour. It doesn't matter if the truck's moving at 600 million miles an hour. We don't add its speed to that of the light leaving the truck. That's the second postulate. The speed of light is the same for all observers undergoing uniform motion. That is, standing still or moving in a straight line at a constant speed. This is an empirical fact. Yes, the speed of light changes when it moves through glass or water, but we're not concerned with these complications. The speed of light in a vacuum is always 670 million miles an hour. It might seem odd, but experiments show this to be true. Now, if you can accept this in the first postulate, you're ready for relativity. They're all you need. Everything else just follows. For our purposes, this means all uniform motion is relative. That is, you cannot determine if you are standing still or moving in a straight line at a constant speed, and the speed of light in a vacuum is the same for all observers undergoing uniform motion. You cool? Alright then. Now for some specialized nomenclature.
Okay, we're going to talk about time dilation in the next, that should be tomorrow's work. So that's it for today, start of special relativity. And like I say, here comes what comes out of that is time is not absolute.